Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a topic from automatic generation control. The name of the topic is block diagram representation of load frequency and excitation control. So this is what is the diagram here we have drawn. In the modern large interconnected system, it is achieved by automatic speed governor system and automatic voltage regulating system. This is the figure which shows the automatic load frequency control, which is ALFC. So this is the part of ALFC, and this is nothing but your automatic voltage regulation, that is AVR loops of a turbo generator. For a small disturbances, the load frequency and the excitation voltage controls are non-interactive with each other. The meaning of non-interactive is nothing but it is independent with each other. This is because for a small change in the active power is dependent on the load angle delta. So please remember, your change in the active power is proportional to load angle delta, that is internal machine angle, and it is independent of the system voltage. And on the other hand, the Q will depend upon the machine excitation, that is voltage, and it is independent of load angle delta. Now this AVR is the fast acting in which the major time constant encounters is that of generator field, which is very small. On the other hand, this ALFC is the small acting with a major time constant involved is due to the turbine and the generator moment of inertia, which is quite large. Now we know by burning the coal, the water is getting boiled up and the steam is passed through the steam inlet. So this will be, we can say, this is nothing but your steam inlet. So when the coal is burned, then the water is getting boiled up, the steam is passing through the steam inlet and then through the turbines. So if you see, this is the steam valve or the controller. So this steam will pass through the turbine blades. In order to have a control over the steam inlet, we have this steam valve. Now, fuel can be coal or the uranium, natural gas, it can be anything. Now, whenever the steam having the proper temperature and the pressure enters to the turbine, which is having the speed, let's say speed will be equal to omega, the power is generated. Now, the sample of the power has been taken here, that is the P. Sample of the power P has been taken from this P plus JQ and which is fed to the grid. The sample frequency F is compared and with we can say a reference frequency. That reference frequency is 50 Hz. So it consists of frequency sensor and the comparator, which in turn controls the steam valve controller. So this is nothing but your steam valve controller. This will be F reference, which is equal to 50 Hz, which is going to be compared with the sample of a frequency which is taken from the power, and whatever will be the error, it is giving to the steam valve controller. So if the frequency is more, then let's say this is suppose 51, this is your 50. So the comparator will give you a difference, which is nothing but your 1 Hz excess will be there. So in this, in order to maintain that frequency up to 50 Hz, the steam valve controller will give a control signal to the steam valve in such a way that the steam inlet will be controlled. If the frequency is low, then the steam inlet is used, and if it is more, that steam inlet will be decreased. Depending upon the frequency, the steam gate gets open or closed. The comparator compare the frequency till F becomes equal to reference frequency, and here the feedback system will operate. Now in case of voltage control, which is called as AVR, sample of the voltage, if you see, sample of the voltage and V reference is compared. So which is going to be compared here. The sample of the voltage has been taken here, which is compared with the reference voltage through a comparator, and the output has been given to the excitation control block. Now the question is, why the frequency control and the voltage control loop will doesn't interfere? As the answer is, as the time constant for the both is different. The time constant of the AVR is more, or we can say it is a faster as compared to that of your ALFC. So please remember, I can write it here. AVR will be faster. This is very important point related to your oral examination. And ALFC, it has a lower speed control. So I can write it at ALFC as a lower speed control. Now, already we discussed that the change in the active power demand, that is a PD, it is dependent on the machine angle. So it is proportional to load angle delta, and it is independent, I can write it here, it is independent of your voltage V. And on the other hand, we discussed that the demand of the reactive power, that is Q, it will be dependent on your excitation voltage, that is V, and it is independent of load angle delta. So I can write it here, active power P is the function of both voltage and load angle delta, and I can write dP by dt, which will be equal to what? It will be equal to, now I will take here derivative, so V as it is, and I will take a partial derivative of delta with respect to time, plus your delta as it is, partial derivative of V with respect to time. So mark this as a equation number 1. Now, as we know, the P is independent of change in the voltage. It is independent of change in the voltage. So I can write only expression as dP upon dt will be equal to V dabba delta upon dabba t, because the P is independent of change in the voltage. So I can mark this as an expression A. Similarly, I can write a Q, that is reactive power. Again, it is function of voltage and load angle delta. And how I can write this change in the Q, dQ by dt? Mathematically, we can write like this. So V as it is, dabba delta upon dabba t, plus delta as it is, dabba V upon dabba t. Mark this as a equation number 2. Now already we have discussed this, that the change in the Q, it is dependent on your we can say excitation voltage, and it is independent of change in the load angle delta. So we can neglect these point or these parameter. So therefore, how I can write dQ by dt? This dQ by dt will be equal to delta dabba V upon dabba t. So take this as a equation number B. Now, change in the active power, that is dP by dt, causes change in the load angle delta, that is dabba delta upon dabba t, and causes change in the speed of the machine. Now the question is, why excitation control is much faster than the frequency control? So this will be your AVR is the frequency, AVR is the excitation control here, and this ALFC is automatic load frequency control. Why it is like this? The answer is, here if you see, the frequency controller must be designed for a slow varying demand. If it is designed for the fast random variations, then the system will be prone to hunting, resulting in excessive wear and tear of the rotating machines and control equipment. Here the change in the load demand is of two types: slow varying around the mean demand and a fast random variation around the mean demand. So the answer for this question is, why excitation control is much faster than the frequency control? So if you see here in ALFC, what you observe, it includes some mechanical equipment, turbine is there. On the other hand, if you see in case of AVR, we have a generator. So turbine has its own inertia, and it takes time to either increase the speed of rotation or decrease the speed of rotation. So that's why here it is observed that whatever the excitation control, that is AVR, this AVR is, we can say, much faster as compared to that of the frequency control. So this is what is the block diagram representation and explanation of load frequency and excitation control. If you have any doubt, please feel free to ask questions. Thank you for watching this video.